We have built the ONOS cluster using 3 Dockers and 3 AutoMix Dockers. Now we have the AutoMix Dockers running in the background. Let's start the ONOS cluster. The IP address of ONOS 1 is 172.17.0.5. The IP address of ONOS 2 is 172.17.0.6. The IP address of ONOS 3 is 172.17.0.7. First, let's log in the user interfaces of the 3 ONOS controllers. Next, let's connect Mininet with ONOS 1 and ONOS 2, but not ONOS 3. As you can see, we did not configure ONOS 3's IP address as the controller address. Okay, connected. The links have also been discovered and shown in 3 user interfaces. Now let's discover the hosts on the network by pingall command. Okay, we can see that the host 1 with IP address 10.0.0.1 is connecting with switch 1, host 2 with IP address 10.0.0.2 is connecting with switch 5. Based on this topology, the shortest path from host 1 to host 2 is host 1 to switch 4 to switch 5 to host 2. Before we ping from host 1 to host 2, let's keep an eye on the flow tables of all switches. The color of the switch's icon matches with its leader controller's icon color. We can see that the leader controller of switch 1, switch 2, switch 3, and switch 4 is ONOS 2. The leader of switch 5 is ONOS 1. Because the ONOS 3 is not connecting with the Mininet, there is no switch under its control. Okay, start the ping. As we can see, the reactive forwarding of ONOS has forwarded and configured corresponding flow entries for the ARP and ICMP packets to make the ping succeed. Because there is no flow entry set by reactive forwarding on switch 2 and switch 3. But there are 2 flow entries on switch 4 are newly configured by the reactive forwarding. The path is exactly the shortest path we expected. We can also tell the forwarding path by checking the packet received data on each port. Because ONOS controller sends LLDP and BDDP discovery packets to the data plane to dynamically discover the topology periodically, any active port will have an increasing value on the packet received field. However, the switch port forwarding any other packets will have an outstanding value of it, so we can tell the forwarding path. Next, I am going to demonstrate the controller impersonation attack on the ONOS cluster. Let's shut down the ONOS 3 to mimic a controller failure. Okay, the ONOS 3 is offline. Suppose there is a malicious ONOS controller called ONOS trying to join the cluster. The ONOS only has limited information about the cluster. Say, it has the same IP address of the offline ONOS 3. Now it is running as a single controller without configuring cluster file. Let's prepare to configure a cluster file to make the path. The ONOS only needs to know one IP address of any ONOS peer in the cluster, instead of the complete set of ONOS IP addresses. And configurates it in its cluster file. Let's restart the ONOS to bring the cluster configuration file into effect and see whether it can join the cluster successfully. As we can see, the ONOS is in the cluster now. That discloses the ONOS cluster vulnerability because the incomplete cluster configuration file with only 2 IP addresses is not hard to achieve by brute force method. Because the mininet does not have a controller with IP address 172.17.0.7 configured, the ONOS therefore only has a role of none in the cluster, which means passively replicating the control plane. As the last but the most important step, we are going to poison the topology from ONOS The goal of this attack is to reallocate switch 3 between switch 1 and switch 4, which will be looked like the switch 2 has changed position with switch 4. The links start to change, and they will settle down after a while. That indicates that any ONOS in the cluster can configure the network even without a direct connection with the network. That is because when the ONOS configure flow entries, it is essentially updating them to its data store. This update will be spread and captured by any ONOS in the cluster, including the leader controller, due to the data store consistency mechanism. The leader controller set up the flow entries on behalf of it, which expose another cluster vulnerability. As a result, the shortest path routing from host 1 to host 2 based on the deceptive topology is no longer through switch 1 to switch 4 to switch 5. Instead, the seemingly shortest path is from H1 to switch 1 to switch 2 to switch 5 to host 2. But there is a switch 3 in the middle of switch 2 and switch 5 not realized by the leader controller. Again, let's prepare to monitor the flow tables on all switches before ping to see which path the ONOS leader choose for the flow from host 1 to host 2. Let's ping from host 1 to host 2 again. As we can see, there are 2 flow entries configured on the switch 1 by reactive forwarding modula. Also 2 flow entries configured on the switch 2 by reactive forwarding. There is no flow entries configured by reactive forwarding on switch 3. Switch 4 does not have the reactive forwarding installed flow entries either. That indicate that the leader controller has chosen the path we induced, and the switch 3 is also hidden due to the fake topology. It is worth noting that the ping works well even though we did not pre-configure a flow entry to patch the gap. That is because the switch 3 is not on the shortest path computed by the leader ONOS. When the leader ONOS received the packet and message encapsulating the ICMP packet from switch 3, it does not know how to forward it, so it let the switch 3 flood it without configuring a flow entry on it. We can also monitor the packet received data on each port to validate our observation. With the time going by, the port forwarding the ICMP packets in reality will have outstanding data on the packet received field. As we can see, the data on switch 2's ports and the data on switch 3's ports stand out from the ones on switch 4's ports. That indicates the forwarding path is truly from switch 1 to switch 3 to switch 2 to switch 5. But it is hard to tell based on the topology view, and the complex real-world network traffic will cover up this attack. That's all. Thank you.